Welcome. Let's go over some programming. First slide says, what is a computer? When we talk about computers, we all think of the black boxes that sit upon our desks or the laptops that sit upon our laps. But a computer is defined as, in a more general definition, as something that takes in some input, has a set of stored instructions that processes the input, and then gives us some sort of output. Think of all the computers that you come in contact in your daily lives from the time you wake up to the time you go to bed. A computer is something that has a CPU in it, called a central processing unit, some kind of memory with stored instructions, and some kind of output. Your phone, of course, is a computer. You can think that your cars have computer systems inside of them. Refrigerators have CPUs inside of them. They even have shoes and cigarettes with CPUs inside of them. These are all computers. Our world is surrounded by computers. That's why we are in such need of computer scientists and people to program these computers. All right, let's go over a few basic concepts. Know the difference between hardware and software. Hardware is all of the things that you can touch. Anything inside of your computer, outside of your computer, anything you can touch is your hardware. Software, of course, is all the intangible items. It's all the things that you can't touch. It's our knowledge that we've placed inside of the computer. Have this visual when we're running a program. Here's our input or our data. Our data can be in the form of keyboard keys or a mouse click or reading from a file. It could even be light input or sound input. Our program runs on our computer, executing a set of instructions to process that type of input, and then it produces some sort of output. History of computers. Computing has actually been around for millennia. Charles Babbage, in a lot of textbooks, is considered the father of computer science, or the inventor of the first computer. Maybe not computer science, but the inventor of the first computer. He used punch cards inside of a machine that he built, which later on people used this same idea to program analog computers and the first electronic digital computers. The history of programming. You're taking this course because you're interested in a programming language. Did you know that there are many programming languages out there in the world? Programming languages to program many different types of computers. If we look at a timeline of programming, we can see that the first programming languages came about in 1943. This was during World War II. You might recognize some of these programming languages as we scroll through them, and you can follow the link to look at them yourself. Here we have Fortran. Is Fortran still used today? Actually, it is. It's still taught at UC Berkeley, and up until a couple years ago was still taught at Merced College. You can still use Fortran to program things. The underlying algorithms of a computer have not changed, and so many of these programming languages still work. Another important programming language is Smalltalk. Here I'm looking at another extremely important programming language, probably the most important language in the world, was our programming language called C, created by Dennis Ritchie when he worked at AT&T Bell Labs. All modern digital devices are usually programmed with some form of C, and all operating systems at their kernel are usually programmed with some form of C. As we move along, and we're searching for Java here, and we're searching for C++, Let's see, C++ came about in 1983 by Bjarne Strustrup, and he took that C programming language and added object-oriented design to it. This is another extremely important programming language that you should know about, and the creator responsible for that programming language. As we move down into the 1990s, this is when the internet boom happened. In 1995, James Gosling, while working at Sun Microsystems, invented the Java programming language. What else was going on during the 1990s? Well, the internet was taking off. The internet needed a platform-independent programming language, and when James Gosling came out with this Java programming language, it fit the bill. It was platform-independent and worked well and was secure. That's one of the reasons that Java became so popular. If we move down, we can also see that JavaScript came out that same year. Another extremely important programming language, it is the language of the web. And we can see that there's still programming languages being created today. And so I asked this question, why do we need so many programming languages? There is only one computer, one set of algorithms it's built upon, which is the binary. One of the reasons that we need so many programming languages is that certain programming languages do different things. James Gosling, while working at Sun Microsystems, tried to use the C++ programming language, and it didn't work for what he was trying to do. So he invented Java. That's usually how all these programming languages came about. The creator was trying to use a different programming language. It didn't work for what they were trying to do, and so they invent their own. Note that Java is not a math-based programming language. You would use something like MATLAB instead. So different programming languages used for different things. Let's look at how a programming language works. We as humans take for granted that we can open a book and we can understand what it says. We process the symbols inside of our brains and decipher and interpret what they're saying. A computer, on the other hand, works on the simplest form of logic. A computer can only execute 1 plus 0, 0 plus 0, and 1 plus 1. A computer cannot even subtract. How do we tell this computer our words and have it understand and do what we want it to do? Well, our choices are, we can write in the ones and zeros, which is really hard to do, but it is how people first programmed computers. Or we make the computer understand our words, which is a much better philosophy and much easier to program this way. So this is how a programming language works. We humans write our program in words. We then take those words and we send them to a new program called a compiler. This compiler works as a translator and translates our high-level language, such as Java, into ones and zeros, called machine code, that the computer can then understand and execute. Here's how a normal compiler works. Notice that it's a C++ compiler. The Java compiler works a little bit differently, and we'll go over that second. Before Java virtual machines and the idea of virtual machines, this is how a compiler would work. Remember that the compiler is a program that is taking our high-level language, our words. It takes as input these words, and it processes them with a set of instructions. It then makes or creates object code. It then takes other object code from libraries that we have imported. It mushes all of that object code together, and it produces ones and zeros, or machine language code that is ready to run and execute on our computer. Compilers translate high-level language to machine language. Remember what source code is the code that we write. An object code is the translated code that the computer can understand. We got to give credit where credit is due. Invention of the compiler was by Admiral Grace Hopper. She was a mathematician, a computer scientist, social scientist, corporate politician, marketing whiz, system designer, and a programmer. She invented the compiler. She said she did this because she was lazy and hoped that the programmer may return to being a mathematician. We got to give kudos to the first digital programmers, which were all women. Men were off fighting the war, and so women were in charge of programming these large machines by actually taking the wires and putting the wires in the correct holes, and in essence programming with ones and zeros. The evolution of programming. I'll go through these slides quickly. There's no real statistics behind this, but they're meant to show a point. When we first started programming, we would program in ones and zeros. This was very difficult, and there weren't many people who could do it, and it was not very efficient. We then figured out that we could program with some words called assembly language. It was still really hard to understand. Not many people could program with it, and it wasn't very efficient. Then came the idea of a high-level programming language. It was suddenly much easier to program. Many people could do it now, but it was still not as efficient as it should be. And then came the dawning of a new era, the object-oriented design era. Hardness level, still pretty low. Many people could do it, but now our programs were much more efficient. Here is where we get all of our games and our software in today's world. It's through the philosophy and science of object-oriented design. We do not learn object-oriented design in this class. You learn object-oriented design in our second level programming course. In our history of Java, we learned that James Gosling, pictured here, was the creator of the Sun Microsystems Java programming language. Sun Microsystems was bought out by Oracle, and that's why when you go and set up your JDK or your Java documents are on the Oracle website. Why choose Java over all those other programming languages? Java is object-oriented, which means it allows one to reuse code. You don't have to write the same code twice. It was built on an object-oriented design idea, and everything in Java is an object or a class. Java has built-in garbage collection. When no references to an object remain, the Java garbage collector automatically deletes the object. Now, what does all of that mean? It means that we don't have to take care of managing our main memory, like programming language like C and C++. It is much easier to program this way. We let the garbage collector take care of releasing memory for us. Java also became popular because it was platform independent. It compiles things different than regular compilers because it uses something called a virtual machine. This means that you could write one program and have it run on everyone's computer, whether it be a Mac or a Linux machine or a Windows machine. 6.5 million developers. Java powers more than 4.5 billion devices. To tell you the truth, I copied and pasted this a little while ago. These numbers are actually higher. Java is everywhere. Let's go over some terminology. SDK stands for Software Development Kit. When you downloaded your JDK, I told you it was a Java Development Kit. The Java Development Kit is a software development kit. Note that since the time Java has been around, it has gone through many evolutions and is always growing and expanding its libraries. I'm going to kind of skip through these Java SDK slides. You can read through them.
So they got me.
Okay, so let's go back to how a compiler is, or what a compiler is. Most high-level languages need a different compiler for each type of computer, and for each operating system, like that picture we saw with C++. Most compilers are very large programs that are expensive to produce. Reviewing how a compiler works, we take our source code, we give it to the computer. The computer uses a program called a compiler to create the ones and zeros that it needs for the computer to execute. The compiler produces machine or assembly language programs called object programs. Here's a picture of how you, as a programmer, would have to write before virtual machines. So with like a programming language like C. You would write your source code for, let's say, a Mac machine. You'd give it to a Mac compiler, and it would make ones and zeros or machine code to run on that Mac. You'd then have to write a completely new program to run through a completely new compiler that was made for a Windows machine. It then would create an executable to run on that Windows machine. And let's say you wanted to include your Linux users. So you would write new source code to run on the Linux machine, use a Linux compiler to compile that code for your Linux machine, and then run the code on the Linux machine. As you can see, you'd had to write 3 new programs. This was very tedious and horrible. There had to be a better solution. And there was. This is how the Java virtual machine or Java programs are compiled. They're compiled differently. You write one set of code called your source code. It goes to a single compiler. That single compiler does not compile it to an executable, but rather it compiles it to something called bytecode. B-Y-T-E. This bytecode can then be sent to any computer that has a JVM or Java virtual machine installed upon it. There's a Java virtual machine for a Mac, and there's a Java virtual machine for a PC, and there's a different Java virtual machine for a Linux machine. You take the bytecode, you give it to the Java virtual machine for that proper Java virtual machine for that computer. The Java virtual machine takes that bytecode, creates the executable, and runs that code on that computer. This was a much smarter way to program because we only had to write our code once instead of 3 different times. So bytecode is the machine language for a hypothetical computer called the Java virtual machine. All modern programming languages today use virtual machines. It's a much better and smarter way to program. So the Java compiler does not translate a Java program into assembly language or machine language. It instead translates a Java program into bytecode. And here's a picture taken from their website that shows a little bit more of the process. So now our programs were portable. After compiling a Java program into bytecode, that bytecode can be used on any computer with a bytecode interpreter or virtual machine. It is platform independent. The interpreter is smaller than a full compiler. The best way to learn how to program is to program. Here's a sample program I want you to program. You could pause the video and copy the code, and you can even copy code from your textbook. But you should try to run a program other than just hello world. Try to run a program like this and make sure you kind of know what it is doing. I understand that you are beginning programming and that you might not understand everything that is going on here. By the end of this class, you will. But you should still type in this code as you see it and still run your program. The more you look at, type, and run code, the more you'll understand it. So try out this program now. You can pause the video and copy it. Or like I said, copy a program from your textbook. The last couple slides are just on some terminology we should all know. IDE stands for Integrated Development Environment. Eclipse, the program that we are using, is an IDE. An IDE is an application that we use to create programs. In my slides, I go over some other IDEs like TextPad and Notepad++, but we are using Eclipse in this Java class. Remember that there is help out there. Lots of users use Java, and so you can go and look up YouTube videos and tutorials, use the internet so that you can learn Java. Last couple slides are on errors. When you first start programming, and even when you're a seasoned Java programmer, you will have errors in your code. Errors are categorized into 3 different categories. We have syntax errors, which you will have a lot of when you first start programming. These are our spelling errors or our semicolon errors. They're errors that the compiler catches and yells at us for and tells us which line the error is on. These are easy to find and fix, and they will become less and less as you get better at programming. Runtime errors are errors that are detected when your program is running, but not during compilation. So in other words, your program compiles and it runs, and maybe it runs 90% of the time or 50% of the time. But some of the time, it does not run and it crashes. A divide by 0 error, when you try to divide a number by 0, is a famous runtime error. Try out that in your code. Try dividing a number by 0 and you can see your program crash. This is a runtime error. Logic errors are the hardest to find because these are errors that are not detected when you're compiling. In fact, your program will compile and it'll run and it never crashes. The only problem is sometimes it gives you the wrong answer. Dividing an integer by an integer is a famous logic error. An integer divided by an integer will always give you an integer, and it'll give you the wrong answer. So 9 divided by 5 would give you the number 1 instead of 1.8. My last slide is some Java in Action links that you can click on, and then good programming practices for naming conventions for your variable names. We'll go over better variable names when we talk about variables next week, but just note that names like final exam score are always better than names like X. This is because if I asked you what X was holding in your program, you'd have no idea. But if I ask you what final exam score is holding in your program, you would know it's holding the final exam score. So names like final exam score are considered better than names like X for our variable names. All right, I'm going to let you go for this week. I will expect that you are going to read and study Chapter 1 and 2, your homework assignments this week, and get your Hello World program completed and attached inside of this assignment. If you have any other questions, make sure you go to discussions and post your questions, or email your instructor, me, or go to my office hours. All right, I will talk to you via video soon.